Swayam Prabha. Digital India. Educated India.
Okay, so now we want to use the other one. This means we will see if I use that as Z in all it, E in all it, what is going to be happen is the E in all it. So I will try to draw the same thing. This is the Z in all it, oxygen and R is the here. On the E in all it, what is going to be happen? This R would be this side and hydrogen will be downside. So we can draw the same one and see what is exactly happening. So I have an oxygen, a metal center, R1, and now this is R1 and R2 in the same side. That means the equatorial and axial I am changing now. So R2 and the hydrogen here, because this is the hydrogen and methyl is. Now this is the bond which is going to be formed with the aldehyde or with the carbonyl group. And this carbonyl is coordinating to this one. And same possibilities when R will put, I will put the equatorial or axial. Obviously, we just understood that if we put the axial, there will be a lot of steric hindrance. So I want to have a more stable directly in the equatorial. So I am not drawing again another one. Directly I am going that this is the most stable configuration. Understood? Because we have already figured out that if this goes to over there, is always have a steric hindrance. Now from that one, what product you expecting? So our bond forming react. So this is become a carbonyl. This is going to form, and that is going to take O minus. So before first we try to draw, as I mentioned, try to draw what is exactly happening. So in this position I have an R2, there is an hydrogen, he's become a carbonyl, that become a R1. At this position that would be the OH, here will be one hydrogen and here will be the R group. Now let us again look for where is the zigzag, so that we can expand it properly writing. So zigzag again we can see it is going up, down, up, down. Okay. So my zigzag is starting from the right side with the R here, and I first go up, I come to this carbon, and what should be the stereochemistry of the OH? I will go to the beta or alpha? Yeah, it should be alpha because the other hydrogen is in the beta. No, between the hydrogen and OH, so this is going to be come down. What is this one? This one should be the OH is the alpha and hydrogen is in the beta. When you come down to here, what is the scenario here? R2 will be the beta or alpha? Beta, yes. So R2 will be the beta. And then I go to the carbonyl and I have a R1. So we have an R1, R2 and OH, and now you can see between these two stereocenter it is an anti-selectivity. So if you take the Z in all it, you get a syn selectivity, but if you take the E in all it, you get an anti-selectivity. Similarly, two anti-selectivity possible. In this one, R2 is the beta and hydroxy is in the alpha, but opposite also possible, that this is beta and this is alpha. How do we get the other one? So this aldehyde is now in the front side. We will place the aldehyde in the back side, and then we will get the other unison as I did from the other one. Understood? Or shall I do it again? Again, one more time. All right. So let's do where I will. Okay, I need this one actually. I'll come back again. Anyway, so first we draw the enolet, 6-member ring. No, this first you figure it out. This aldehyde, and between these two, which one is in the front side and which one is the back side? Enolet in the front side or aldehyde in the front side? Front side. In from you, which one are you seeing first? And back side? Enolet. Now I am going to draw where the aldehyde will be in the back side and the enolet will be the front side. Okay. So let's draw the enolet first. So we can have a enolet as it is. There is no problem. Okay. And now I am going to have a 6-member ring. No. So this is going to be react, and then so maybe nicely if we want to draw. So I will have a here metal, and your aldehyde I am placing in the back side, and that's why this R is above the bond. And the hydrogen and the R. Now you see, which one you see at the front? Enolet, and the aldehyde in the back side. Yeah, that's exactly what I am trying to say. And now you are going to make a bond between these two. So you follow the arrow, enolet comes back, these bond form, and that become a OM. OM, when you add the water at the end of the reaction, become OH. So again we follow the zigzag. First we draw whatever the bonds are forming and what are the bonds are breaking. So I made this bond is formed, and from there I have an R, hydrogen, and the OH, correct? I come to here, I have a R, I have a hydrogen, and then I have a carbonyl. This carbonyl has a R. Now I have to expand it in a zigzag format. Before that I need to find out where is my zigzag pattern. So I am starting with the R, I go up, I come down, I go up, and I will again just stay there and will change it. So my zigzag is starting from the left side. You remember in this zigzag starting from the right side. So I would have R. From the R I should go up or down. So my major axis is going to be up. When I go up, I have a hydrogen and OH. What will be the scenario? OH will be the dotted or hydrogen will be the dotted? OH will be the dotted because that's the downside, and hydrogen in the beat. Actually I am not showing hydrogen. By default that means this is this one. Understood? That you got all understood? No, only one is enough. Now when I come to here, I go up, I came down. When I came down, what will be the R scenario? R dash dash or hydrogen dash dash? R dash dash. Hydrogen dash dash. So R should be there. Beta. No, in the in the chair form, this is in the upside. No, this is in the downside. This is on the chair form of the right point. So this is the beta, and this is the downside. Okay. Now I go up, I see the carbonyl, and this is just, you can have a simply a rotation because there is no stereo center. I give the R group here. So what you get now? So I remove this one for the clarity. So what we have between these two center? So you can simply, now we cannot directly compare between these two because this RCO starting in the left side and that is RCO starting in the right side. So I R1, R2, yes, that is true. So, from where we are going? From the first step, this is the R1, R2. So, that means this is the R1, this R2, R1, R2, perfect. We got that. Now, this one, R1 is starting something, we have made a mistake. I think we get it wrong. No. You see, this is the R, is not a numbering. This is R2, this is R1. This is the R, R2, R1. Now is correct. Now, I just want to make the same thing, just I do the flip of this one, such that the R1 CO comes both in the right side and we can compare. So, it is molecule was like this and you just like this, out of plane flip. So, in that case, I get a carbonyl here and R1. Then when this goes there, R2, that will be the downside. This one would be the upside and then R1. You see, in this case, this is also anti, this is also anti, but in this anti, this is down, this is up. In this anti, this is up and this is down. Okay, both are enantiomer. So, we are very clear about that, how we understood now so far that we know how to make the E enolate and the Z enolate, and we now also know how the E enolate gives the anti product and Z enolate leads to the syn product. And so, this is model we call a Zimmermann-Traxler model, the 6 member. So, it is called Zimmermann-Traxler chair like transition state. Okay. Now, I have given you a couple of enolates, lithium enolates, boron enolates, silyl ether, we will see that one later. The question is which enolate would be very good. So, that we can figure it out, and usually imagine that this bond distance, this metal when is coordinated with the oxygen, so they are making a bond. Now, imagine that bond is very close or shorter bond. That means this transition state will be more tight. If you have a more tight transition state, you will expect to be a higher selectivity. Okay? If the loose transition state, axial equatorial will try to change it. But if it is a tight transition state, once it's formed, it's fixed, it can't move. Okay? So, this is the key part, that how the bond distance is matter. Okay? So, I have the data, let us say the M and the oxygen bond. So, when M is equal to a lithium and oxygen, so that bond length is 1.9 to 2.0 angstrom. When it is the magnesium, so that's become a even bigger 2.0 to 2.1 angstrom, and when it is a boron oxygen, this is become a shorter 1.4 to 1.5 angstrom. So, now we can easily imagine that if the boron oxygen bond is very short, this transition state will be even more compact, very tight transition state, and very high selectivity is going to be expected. That means, if you use the boron enolate, your syn anti will be very high. Maybe if you are expecting that will be maybe 99:1. But if you use the magnesium enolate, if the bond distance will be high, you get still maybe selectivity, but the ratio will be slightly low, maybe 90:10. So that is what I am trying to make. So this is the boron enolate, which is actually make the whole things very important. Now one more enolate is there, or one more important things. Okay, another one thing I just going to say, you have familiar, I think already you have a stereochemistry class that the C phase and the re phase, C phase and re phase. So if I draw an aldehyde, let's say I draw an aldehyde, hydrogen R, the front side is a re phase or C phase? So how do you, so usually we give a one number here, the next priority number 2 get R, and then the 3. So 1, 2, 3, the front side is the S, anti-clockwise happening. So that is a C phase. Or you can take the other one, let's say this aldehyde, then R and hydrogen. Now this is 1, this is 2, and this is 3. Now the front side is a clockwise, and so this is a re phase. So when the aldehyde is going to react, I have already told the enolate can come on the front side or enolate can come on the back side. That means this aldehyde actually facing the enolate in the two different phases. For example, if this is the front phase, I say the C phase, then the back phase is the re phase. Now tell me, in this particular configuration, which phase of aldehyde is reacting? Re phase or C phase? Okay, let's try to numbering and see. So this is the number 1, this is the number 2, and this is number 3. So 1, 2, 3, which we are seeing is the re phase, but that re phase is not reacting, because re phase is this side, reaction is happening from this side. So that means is the C phase of the aldehyde is reacting, correct? So I can say here, so now we make a rule actually. So in this particular case, what we have, the C phase of aldehyde is reacting of aldehyde. Similarly, enolate has also phase. Okay. So in the enolate cases, let's say some R and hydrogen, and so this is the 1, this is the 2, and this is the 3. This center is going to react for the enolate. So it should be 1, 2, 3. The front side, whatever you seeing, is the re phase, and the back side, whatever you seeing, is the C phase. Now you tell me, in this enolate, it is the C phase or the re phase is reacting? Let's we can figure it out. So this is the number 1, and this is the number 2, and this is the number 3, correct? So number 1, number 2, 3. So C phase, that phase is actually reacting. So this means it is the C phase of enolate is reacting. Now if the C phase of enolate is reacting with the C phase of the aldehyde, CC, same, it will be the anti-product, because that's what you're getting, the anti-product. Okay. So I can make a short rule that if the C phase of the enolate is reacting with the C phase of the aldehyde, I will get the anti-product. Okay. Not only like that, Even also if it is a re-phase of enolate is reacting with the re-phase of aldehyde, I would also get the antiproduct. The same combination of the phase happen, it gives the antiproduct. That means the other combination, that means the re-phase of the aldehyde and the C phase of the enolate, or the C phase of the enolate and the re-phase of the aldehyde will give the syn product. So, I have erased that, but I can figure it out from that. Let us see what we have. Imagine that we can, I need to draw again, that is what is the problem. Okay. So, I change this one to the hydrogen. Okay. So, that means R2 hydrogen. That means R1 CO, R2 should be the, no, I made the same thing, hydrogen R2. So, the R2 should be the down, correct. Now, I change this one. Now, you tell me which phase of aldehyde is reacting. First, you say the aldehyde. Huh? So, 1, 2, 3, this is re is outside, that means C phase reacting. So, I can have a again the C phase of aldehyde reacting, and that is reacting with the which phase of the enolate, because this is now 1, this is now 2 and this is the 3. So, the re phase of the enolate. So, C phase of the aldehyde is now using the re phase of the enolate. If that is the case, we are getting which product? We are getting the syn product. Okay. So, you get a syn product. It is also the same other way also. That means the re phase of the, if the re phase of the aldehyde and the C phase of the enolate, that would also lead to the syn product. Okay. In the exam you have seen sometimes they ask two compound in the CSI and NET exam, and then they ask which phase of aldehyde is reacting to the which phase of the enolate and what should be the product in that cases. So, you can easily figure it out from this kind of transition state. Okay. Now, we are going to move to the silyl enol ether cases. So, this is the normal metal enolate, lithium, magnesium, boron, all these things are fine. Now, we are going to the silyl enol ether cases and what is exactly going to be happen. So, we have already figured out, or we have already seen that in the silyl enol ether cases, we can have also two of them, that OSIME3 or maybe R1, R2 and then R1. So, this is my Z enolate or silyl enol ether, this is my E silyl enol ether. Okay. I am going to react with some aldehyde, let us say I will react with the benzaldehyde, no problem. Any aldehyde you can take, R aldehyde is fine. And this reaction usually you need a Lewis acid. Without Lewis acid usually not work, because they are not very strong nucleophile like enolate, they are weak nucleophile, your aldehyde has to be activated. And typically you can use titanium tetrachloride or tin tetrachloride or BF3 ether, all kind of option you have. And in this particular case, this is the Z enolate. So Z enolate usually what product we get? So we can directly also write the syn product in this case. So you get a, this is the going to be happen. So what you have? So you have a silicon oxygen bond comes and then that react to the aldehyde. So you get a R2 and you get an OH phenyl, and this is supposed to be the syn product. That's what we are giving. So this again a racemic compound means you also have another one. That means these two are the alpha. Is that clear to you? So I am not drawing again that one. So this is the syn product. So this is we have a syn product. Now the same reaction when you are going through the E enolate or E silent ether, what are you expecting? Here is not the case. This will also give you the syn product. So other enolate like a lithium enolate, boron enolate, they have this selectivity. E goes to the anti and Z goes to the syn. But silent ether cases, whether you start with the E or you start with the Z, it doesn't matter. You always end up to the syn selectivity. So what is exactly then happening? I said the previously the selectivity is coming from the Zimmermann-Texler transition state. That means this reaction is not following Zimmermann-Texler transition state. If it is have been followed, we should get the similar reactivity. So then if it is not following, you remember that HMPA cases that which is not forming 6-member transition state or 6 chair-like transition state is going to the open transition state. It is exactly the same thing is happening here, that this is going through a open transition state, okay, and this reaction is called Mukayama-Aldol reaction. Mukayama-Aldol reaction. So previously we have a classical Aldol reaction. Now silane ether is used in the Aldol reaction. We call it the Mukayama-Aldol reaction. In the Mukayama-Aldol reaction, your reactions follows an open transition state, and we want to see now how is going to be happen. Okay. So first I just give you a draw, and then I will really draw how it exactly happening. So let's imagine that this is the carbonyl, okay, and this carbonyl carbon will react with this particular bond, this particular carbon center. No, so that I am drawing this carbon, and I am taking the Z enolate. Okay, so I just put the, let's say Z means R2 OSIMe3 and R1 and this hydrogen. Okay, so let me make this one like this, and I cut it. Sorry, this is the water. So you understood that this haldehyde is in the front side and this one is in the back side, and which two bond is which two center is going to be connected? So we are going to connect this center. So this one is going to react at this position, correct? Because that is the silane ether position. This is going to react at this position. Clear to everyone? Now I want to draw this one in a sawhorse to understand much more clear. So in the sawhorse I am looking from this side, okay, not sawhorse, I will draw the Newman projection. If I looking from this side, I see the carbonyl and I have a double bond hydrogen and the phenyl. I see the back carbon, which is the back of that has a hydrogen and that has a R2. So I would say the hydrogen and R2, and then a double bond is coming down. From there, OSI Me3, and we have a R. Actually, we are following R1, R2, no? This is R1, this is R1. Is it clear to draw to understand how we got it? Now the reaction happened, this means this goes and then this reacts. So when it reacts, this become a OH. So that lead to, when the reaction happens, so that led to what? This become a OH, correct? This become a OH. This hydrogen and this R2 will be as it is. So this hydrogen and this R2 as it is, and then this become a single bond, have a carbonyl and the R1. That is what we will get. Now, which phase of silyl ether is actually reacting? I can draw another one also. Right now, this is also cis, but you can rotate the other way also, where these two would be other way. So what I am trying to say, that I can draw another one, hydrogen, phenyl, and then this is the R2, this is the hydrogen, this is the R1, this is the OSI Me3, correct? This is also Z enolate. This is also Z, this is also Z. One time it was like this, next time I draw like this. Now if I try to draw this one here, let's see what exactly happened. So again the same aldehyde first I put on the things. Now which bond, which one is actually bond forming from this center to that center? So I would give that this is now R2, this is now hydrogen, and then this is a double bond which have a R1 and OSI Me3, correct? So you get two things, these version. Now you tell me which one will be favorable. Both is possible. Both is the same sin. This is also Z enolate, this is also Z enolate. Yeah. And so between these two, which one you think is more favorable? First one very obviously, because you are really putting a lot of steric hindrance between these two. And now in this case the two bulky group is actually far away from each other. So that means this is not going to be formed, or I would say this will be the favor. This will be the favor process. Now if that is the case, let's see, parallelly we can go such that we can see how it is exactly happening. So what I will get, hydrogen, OH, hydrogen, I got R2, hydrogen, carbonyl and the R1, correct? Or you can see both are the same actually, you just, because now it is a single bond, it can easily rotate, carbon, okay? So this one I want to now draw in a zigzag, okay? You have to be very, very careful now. How do I want to have a zigzag? Where we are seeing the zigzag? In the zigzag, your first job is to find out a long chain in the long chain. So I would say that main long chain will be this and this one. So what I will do, the back carbon I slowly rotate such that I get the phenyl and this group in a linear form. Correct? So what I am trying to say, that I keep that phenyl hydrogen OH, and now I am rotating the back carbon, bring this one to the here, CO R prime, R2 goes here and H comes to the down. And now there is a bond between these two. In this bond, if you see, this is a linear line, and R2 and OH in one side and both the hydrogen is in the other side. So that means this is leading to a syn product, because both R and OH would be the beta beta or alpha alpha other way. So if you do that one, so I will have a phenyl, I am going up, down, up. So when you go up, I see the OH is in the beta. When I come to the down, I see the R2 is also at the beta, and then I got the COR. So you get again a syn product, both of the syn stereochemistry, and we get this particular compound. Now if you see here, what we will get in this particular cases. So again we rotate and bring it to the long, so that we can get a long change. So OH, phenyl, hydrogen, this group I bring it to the COR, COR1, COR1, and this become a hydrogen and this become a R2, correct? And now you see the R2 and OH is the other side of the your long chain, and so it will give you that phenyl, OH is the beta, I come down and I see R2 is the alpha and CO R1, correct? And this is the anti-product, and this is not going to be formed, so not forming, not form, and this is the major form for this. Well, what is the fun it here? Because we know Z is supposed to give the syn product. The most important part is that I need to now show that I start with the E and I go to the Z or syn product. So that we have to now figure it out whether that is the case. We are crossing the time, but this is the last one. Next I will continue. Okay. So now I am going to have a E enolate between these two. The same thing I am going to operate, and you can simply think about that okay, is the same reaction hydrogen phenyl, and at this point I need an E enolate. Okay. So E enolate means I can have a R2 here and a hydrogen here, and E means I have to make R2 and O silane ether is opposite. Correct? This is conformation is correct, or just position, and the reaction is going to be happen between that center to this center. Let's draw again in the Soho Newman projection formula, and this is not hydrogen, this should be the R1, no? Okay. Similarly, as I did here, you also have an option that you flip it this way. That time R3 will be here, and you will see there will be steric hindrance, so we will not consider that one. So I am not going again that. So this is the most favorable one. Now, if that is the case, so let's the reaction happen. If the reaction happen, I get the OH, I get the phenyl, hydrogen, this hydrogen R2, a carbonyl R1, correct? Now, I make the longer chain, that COR I will bring to here for a rotation or via rotation. So, OH, phenyl, hydrogen. Now, this group come to here, COPH, R2 here and the hydrogen here. Understood? I have rotated that. And now, that one, no? And from there, what should be the scenario? You can easily see that R2 and OH again in the same side of your sense. So, this is a scene selectivity is coming. So, eventually I can start with the phenyl. I go up, I see the OH come down, I see the R2 also up and then R1. You see, that is the things I was telling. I started with the E enolate. This is the E enolate. You can see is the E enolate. Once I put in the Newman projection and rotate, eventually product become a syn product. So, that is what we are trying to say. In the Mukayama-Aldol reaction, either you start with the E enolate or E silanol ether or G silanol ether, it does not matter. It will lead to the syn product. Okay? Alright. So, we will stop here.
SwayamPrabha, Digital India, Educated India.